Okay, so one of you won that game of bingo, but you didn't. There was one winning card out there, all right. So we'll just share the jellies. Now, so that's the binary system, and in that system, every bit, the position of the bit tells you how much it's worth. And typically in such systems, the one at the right we call the least significant bit, and the one at the left we call the most significant bit. Okay? So with a system like this, with 8 bits, we could represent all possible values from 0 to 255. We have 256 values in total, but the bottom one being 0, the top one would be 255. So the next question then is, how might we represent positive and negative integers? What kind of a system could we devise to... I don't just leave it thrown around. If you're the last one, put it in your pocket and put it in the bin or something. No. So how might we devise a system where we could represent positive numbers and negative numbers? And when I say how might we devise, I mean it's as simple as that. We are making this up. Now people have made it up before us, and they come up with some good ideas. But there's no like Moses didn't come down from the mountain with a system, delivered from God. People just made this stuff up. So there are some things that are by convention the way to do it. But you could have any system that you like. How might you represent negative and positive numbers? Well, I'm talking now not about decimal numbers, not about real numbers. I'm just saying, how would you have, here we can go from 0 to 255. How would we do if we say if we needed to represent minus 10 or something? Or minus 19? What might we do? Well, one thing we could do is we could use one of the bits for the sign. So we could have one bit at the start. No, it could be at the end or the middle as well, but at the start. And we could make that special. And that bit would tell us whether it's a positive number or a negative number. So we could say if it's 0, it'll be positive, and if it's 1, it's negative. Or we could say the other way around as well, vice versa, whatever. It doesn't matter. So then we could have something like this number here. We have 8 plus 2 is 10. And because this is 0, it's positive. So that could be positive 10. And then we could say here we have the same number, but the first bit has been flipped. And because that's a 1, we'll say it's minus 10. So we could represent positive and negative numbers this way. We could say here 26 is 11010 with a 0 in front of it. And we could say minus 26 is 11010 with a 1 bit in front of it. And that could work quite well. And we call a system like that sign plus magnitude. So the first bit gives us the sign of the number, and then the magnitude then is the rest of it. Here, 00000 with a 0 in front of it is positive 0, and 00000 with a 1 in front of it is minus 0, which is 0. Now that's not particularly attractive. Having two ways to represent 0 isn't especially attractive, but it's not the end of the world. But obviously there's no difference between positive 0 and negative 0. Big difference between minus 1 and plus 1. The difference between minus 0 and plus 0, there isn't one. Okay? And a system such as this could represent values from minus 127. If you had 8 bits and the first bit was the sign, you could go from minus 127 to plus 127. Would that be right? It's 255. No. So a system like this is very easy to understand. and even looking around at your faces, I think it is easy to understand. It's very easy to implement, okay? It's unfortunate that there are 2 sequences for 0. That's not terribly satisfactory. If you had a shopping list of, features that you wanted in your numbering system, that certainly wouldn't be on it. But it's not a deal breaker. And it's not very useful. Now, I'll explain what I mean by useful in a minute, because we're going to look at one that's more useful. There's another system called ones complement. And what you do with ones complement is you take the positive number and you can obtain its negative equivalent by flipping all the bits. Okay? So here we have a number, whatever it is. You could work it out. You flip all the bits, you get the ones complement. That's easy to understand, and it's easy to implement. It's a bit more useful than sign plus magnitude. Bit of a typo there. Now it still has 2 zeros, because you could take 1, 1, 1, 1, 1. Like all the ones and all the zeros both stand for 0. One is positive 0, one is negative 0. So that's unfortunate. But it does allow numbers to be added together using binary addition. And you can't do that with sign plus magnitude. So if you were to take, in the sign plus magnitude system, if you were to take something like, here we have minus 10 plus 26. If you did a binary addition of those, you wouldn't get anything like 16. Whereas with ones complement, you can do a binary addition on the values and you can get an answer that makes sense. So here we have 3 plus minus 4 in ones complement. And when we add them together, we get 1, 1, 1, 1, 0, which turns out to be the ones complement for 1. Sorry, for minus 1, which is what you would like. So 0, 0, 0, 0, 1 is 1. 1, 1, 1, 1, 0 is minus 1. So if you take numbers in the ones complement system and you add them together using binary addition, you actually get the right answer, which is a pretty big deal. That's very, very handy, because it means you're not going looking up what the things should be. So it means you can perform maths on the numbers and everything would be okay. You can also do the same with subtraction, but that's more complicated because of something I'm going to show you in a second. Now, however, if there's a carried bit at the end in ones complement, you have to feed it back in. So here we have like 1 plus 1 is 0. Sorry, 1 plus 1 is like 10. It's 1 carry 1. But it's binary now, right? So I'm going to like binary addition. So 1 plus 1 is 0 carry 1. 1 plus 1 plus 1 is 1 carry 1. And 0 plus 0 plus 1 is 1. Then here, 1 plus 1 is 0 carry 1. And then we have 0, 1 plus 1 is 0 carry 1. That carried 1 there at the end has to be fed back in around here. So that 1 has to go in there. So it's that can be a bit tricky. So the system does work, but when you do the addition, if there's a 1 left over, you have to carry it back in around the back to get the correct answer. And so here, 11 plus minus 4 equals 7 is the correct answer. You can also do subtraction as well, but that involves borrowing and all sorts of carry-on. So this has most of the features that we'd like in a number system for positive and negative integers, but there's one or two things that aren't so desirable. Which brings us then to a nicer system. Okay, so with 1's complement, we're still not happy because that wrapping around that 1 bit is a bit of a pain. It causes problems. It's just hard work. And also, you still have 2 values for 0. You still have 0, 0, 0. All the zeros is 0 and all the 1s is 0, which is not great. 2's complement is very, very like 1's complement. Okay? To get the 2's complement of a positive number, you flip all the bits, as you do with 1's complement, and then you add 1. So if we have the number 0, 0, 1, 0, 1, 1, 0, 1, we flip all the bits, we get 1, 1, 0, 1, 0, 0, 1, 0, and then we add 1. So in this case, it would be 1, 1, 0, 1, 0, 0, 1, 1. And so that's the 2's complement. So it's 1's complement with a bit of a twist at the end. Now, 2's complement allows numbers to be added together simply enough. So here we have the binary value 0, 0, 0, 1, 1, which is 3, positive 3. If we're looking for minus 4, that would have been 4, right, which would have been 0, 0, 0, 1, 0. You flip all the bits, you get 1, 1, 1, 0. No, you would have got 1, 1, 0, 1, 1. When you add 1 to that, you end up with 1, 1, 1, 0, 0. And so when you do the binary addition with that, you still get the correct answer. What's nice about 2's complement is that you don't have to deal with the carried 1 that falls off the end. That just goes away. So here we have 11, which is 0, 1, 0, 1, 1. So it's 8 plus 2 plus 1. That's right, isn't it? And then here, once again, we have the value for minus 4. When we do the binary addition there, we get 1, 1, 1. Here we have 1, 1, which is 0 carry 1, which is 0 carry 1. But this carried 1 at the end here just goes away. Unlike 1's complement, where you have to bring it around and feed it back in again here. Okay? So the carried bit there can be ignored. So in terms of implementation, if you were doing this in, writing you wouldn't write a program for this, but if you had a piece of silicon to do this, it is a bit simpler. And there's only one way to represent 0. Because if your regular 0 was all the zeros, if you flip all the bits, you get all the 1s. When you add 1 to that, you get all zeros. So there's only one way to represent 0 in 2's complement. So that's very handy. Any questions on that? So let's look at the 3 systems we have so far. Plain vanilla binary for positive integers. Sign plus magnitude, much the same, except you have a bit at the start to tell you whether it's positive or negative. You can't add them together to get what you'd want, which is unfortunate. But with 1's complement, where you simply flip the bits to make the negative number, you can perform binary addition and get correct answers come out, although you do have the complication of having to deal with the carried bit. 2's complement is basically 1's complement, which is inverting all the bits, and then adding 1. And when you add them all together, it does work out. You can do binary addition and subtraction just like you would, and everything works out fine. And there's only one value for 0. Now, there's another system then as well you could use, which is just offset binary, sometimes called XSK. And in this one, what you do is you've basically got so many slots. You know, if you've got 8 bits, you've got 256 slots. If you've got 5 bits, you've got 32 slots, isn't it? And you just basically make all the zeros represent the lowest value in the range, and all the ones represent the highest value. So you could have something like 0, 0, 0 is minus 3. Next one up, 0, 0, 0, 0, 0, 1 is minus 2. 0, 1, 0 is minus 1. 0, 1, 1 is 0. And just like that. So you just have a range where you start at the bottom and work your way up to the top. Now there are times you'd want to do that. The main time you'd want to do that is when the values you have aren't oscillating above and below 0. Like if you need to represent a range of values, you know, between minus 64 and plus 64, probably should have said between minus 63 and plus 63, then, you know, 2's complement or sine plus magnitude is probably the way to go. But if your values might range from minus 50 to plus 10, well then sine plus magnitude would be wasteful, because you'd be making space from minus 50 to plus 50, and you'd be wasting 40 up there that you're not using. You go from minus 13 to minus 6, the same way. Any questions on that? What I like about all of these things, well, apart from 2's complement, is if you were stranded on a desert island that somehow had loads of binary communication systems, you would probably come up with all this. You know, it kind of makes sense once you know it. You think, but yeah, sure, how else would you do it like? Do you know? Apart from 2's complement, I would have died an old man on that island before I'd have come up with 2's complement. That's just downright clever. But 1's complement would have dawned on me. And so this is what this module is about. How do we make bits represent different kinds of values? Now, representing decimal numbers then is a whole other thing. So if you need to represent, you know, 42.927016 or, you know, 53 million so many thousand whatever 0.74201. That's a whole other story then. I mean, you could say, well, we could have a bunch of bits representing the numeric, the whole number part, and then a bunch of bits representing the decimal part, and we could have sort of a presumed or implied decimal point between them. And you could, I suppose you could make something like that work. Yeah, you know. But for most applications, we actually use something called floating point. And this has been developed over time. And there's a standard and there's a format developed by the IEEE, which is the Institute of Electrical and Electronic Engineers. That's a professional body for electrical engineers. And so that body developed a format which ultimately became a standard. And so most computing systems represent decimal numbers or real numbers as us computer scientists call them, using the IEEE floating point system. Now, within that, there's a couple of variations in terms of the level of precision that you need. But when you're representing real numbers, the only question you have to ask really is, are you using IEEE floating point, or did you make something up? And most people use IEEE floating point. I considered telling you all about that and decided against it. So if you're really interested, you can look it up. So IEEE floating point is what we'd use for decimal numbers. And obviously, the more bits you have in your number, the more precise it can be. So sometimes, from time to time, you hear of some scandal where people over the lifetime of their mortgage were charged, on average €3,000 more because the bank had some mad rounding error or something like that. That's typically an issue with the representation of the floating point. So sometimes you need a lot of precision. If you go into pennies, you don't need that much precision in terms of the price of something. Generally, although it says 3.99, it's actually just an integer value in reality because it's 399 pennies. But, someone's height could be a real value. Do you know what I mean? No, it doesn't fit into discrete chunks. But, they don't put on your driving license or on your ID that you're 1.832596742 meters tall. We don't need that level of precision. If you're launching a rocket at the moon or at Mars, well, a centimetre here or there, by the time you multiply it, the distance to Mars, could be a lot. So in some applications, you need an awful lot of precision. In others, you don't. And that's one of the things we're going to be looking at in this module a small bit as well. For many things, you can use a bit less precision and get away with it. So the more bits you have, the more precise you can be. That's the takeaway from that, but I don't propose to go into the details of the IEEE format. But depending on the kind of number you want to store, you can use different formats. Any questions? So that's all I have for you today. And I'll see you in the lab in a little while after you've had your coffee.